What happens when you replace the feedback resistors in an inverting amplifier with diodes? I'm Professor Fiore, and I'm going to explain it to you right now. Well, the answer to that query is you get log amplifiers or anti-log amplifiers. What's the deal? What is an anti-log amplifier? What's a log amplifier? Essentially, these are circuits that are used to either compress or expand the range of signal from something like a sensor. In other words, we're going to map, let's say, a given range onto a much smaller range. That would be a log amplifier. Or we're going to take a given range and expand it to a much wider range. That would be an anti-log amplifier. Very often you do this to compensate for the fact that your sensor is nonlinear. Now, a way to remember this is to just consider this whole log-anti-log function in terms of, let's say, doubling or increasing by a decade. Factors of 2, factors of 10, something like that. So as an example, if you were to use a log amplifier and you doubled the input voltage, and I don't care if you're going from 100 to 200 or 200 to 400 or 300 to 600, you double it, your output on the log amplifier might be 30 millivolts. Right? So you double it, up 30 millivolts. You double it again, up 30 millivolts. You double it again, 30 millivolts. You can see how that's going to be compressive. The flip of that would be the anti-log amplifier. In other words, I increase my input by 30 millivolts and the output doubles. I increase it by 30 millivolts again, the output doubles again. I do it another 30 millivolts, it's doubled again. You can see how that's going to get big really, really fast. Now, probably the more important part of this video is sort of reminding you of the characteristic of a feedback amplifier, which is the overall response of the amplifier is reflected by the characteristic, the current voltage characteristic of the items in the feedback loop. So if you have resistors in the feedback loop, and that's all you have, just resistors. You know, resistors have a nice linear current voltage characteristic. And the end result is you end up with a system that's a nice linear amplifier. On the other hand, if you were to use, let's say, a capacitor, which would have a current voltage characteristic that would be a derivative or an integral, depending on how you write it. So a derivative, you would say I is equal to C times dV dt, the rate of change of voltage with respect to time. That sort of derivative or integral characteristic, right, if you wrote it in terms of V rather than I, that characteristic can then be used in the feedback loop to create a differentiator or an integrator. In other words, a circuit that differentiates the input signal or integrates the input signal. Another useful device, and that was the sort of the building block of the old analog computers from days gone by. But you know, we still have uses for these things. So in order to obtain a log or an anti-log characteristic, then we need a device that has a logarithmic current voltage characteristic. The first thing that probably pops into your head would be a standard junction diode. You could also use a BJT, a bipolar junction transistor. I'm going to keep this simple and just look at a diode. That's it. So you've got two options. You take an inverting amplifier, you either throw it in the RF position or you throw it in the RI position. If you throw it in the RF position, you're going to get a compressive or logarithmic style amplifier. If you put it in the RI position, it's going to expand the signal and you're going to have an anti-log amplifier. Typically, these are set up to be unipolar. In other words, they'll only accept an input voltage of a particular polarity, either positive or negative. Flipping the diodes will take care of that, whether you want a positive or a negative input. All right, so I'm going to stick again with these fairly simple circuits, but I want to warn you up front. By themselves, these circuits have some issues, one of which is they're highly temperature sensitive. They're not super stable in that regard. There are some other issues I won't get into, but it's enough that you could sort of play with this. One of the nice things about using the simulator is that you don't have to worry about device matching, right? When you throw in a particular diode model, well, if you use multiple diodes, they're all exactly the same. In the real world, matching your devices is an issue. So if you're going to use something like a bipolar transistor, you can buy, match pair transistors, and that will help you. But again, I'm just going to stick with these sort of simple introductory diode circuits. So here I have up front my log amplifier, and that's feeding an anti-log amplifier. Now remember, these are inverting amplifiers, right? There's the little inverting sign. So normally it'd be RI and RF. I've thrown the diode in the RF position. This is a log amplifier, and this is going to compress the input range, but also invert it. So I'm going to have negative voltage. So what I've done with my anti-log amplifier is I've flipped the polarity of the diode. If I had a positive input voltage here, the diode would be going in the other direction, right? If I wanted negative input voltages, then this diode would be going in the opposite direction. All right, so because it's inverting, I just flipped this. Why did I put them both up here and cascade them like this? Because since these things are perfectly matched in my simulator, notice I also have identical resistors, and that's important. What will wind up happening is that I'll get the log of the input at this point, and then I'm going to take the anti-log of that, which should give me the original signal. In other words, this output that I've labeled log-anti, right, log-antilog, should be the same as whatever my input signal is, right? I go through a process, and then I undo that process, essentially. Take the log of it, take the anti-log of it. Boom, here we are. All right, I'm going to just stick with DC inputs just to show how this thing is compressive. All right, so the input voltage is 1 volt. Let's see what we get for V-log, and let's see if V-log anti is, in fact, what we started with, 1 volt. So we don't have to do anything fancy here. We can just do a straight DC analysis and see what we get. All right, well, right off the bat, this is 999.8338 millivolts, so this is virtually the same as the input. All right. I will note that I have used BiFET input op amps over here, so they have very, very, very tiny input bias currents, and that's going to help with the accuracy on this. This is one of those things that can kind of throw your log amplifiers and anti-log amplifiers, for a loop, so to speak. In any case, our output here is a negative 401.8. Let's just call it, it's approximately negative 400 millivolts. Now I'm going to turn around and crank this thing up by a factor of 10. So I'm going to put in 10 volts. So if this was a normal amplifier, instead of, going from 400 millivolts, I would go up to what? 10 times the input, 10 times the output. I'd be looking at around 4 volts. But this is compressive, so I don't expect to see that. In fact, I only see 500 millivolts. So it's only gone up about 100 millivolts. A smidge more, but, about 500 millivolts. Okay. What if I go the other way? So let's put in 0.1 volts. Again, if this was a normal amplifier, this signal would, drop down by that same factor, right? Put 1 volt in, got 400, put 0.1 volts in, we should get, 1/10 of that, right? 40. Let's see what we get. All right. Notice V log anti is still tracking perfectly here, right? Now, 299.4, I think we can call that just about 300 millivolts. So the factors of 10 on the input are turning into about 100 millivolts over here. So I went from 100, I got about 100 millivolts, I got about 300 millivolts. I put in 10 times that, 1 volt, I got about 400 millivolts. And then I put in 10 times that, 10 volts, and I got, only 100 millivolts again. Now we can keep doing this with all manner of different voltages and whatnot, but you don't have to because I've already done it for you. Here's a nice table. I put in a whole bunch of different voltages and I've checked the various jumps, so to speak. Little warning over here. The first three, the 100, the 50, and the 25, this is no problem feeding these signals into the log amplifier. But if you actually build this in your simulator and try it, you will find out that the log anti output won't track. In other words, when you look at this signal, it's not going to equal the input. Well, think about it. I'm running on 15-volt power supplies. There's no way if I put 100 volts in here, I'm going to get 100 volts out here, right? This op amp is going to saturate. Period. The end. But other than that, you actually get pretty darn good matching as you go through here. Anyway, let's just do some real quick checks. Go from 100 volts down to 10 volts. That's a 10-to-1 factor. I'm going from 604.5 millivolts to 503.2. And I've just made some notes over here, right? If you go from 100 to 10, the change is 101.3 millivolts. If you went from 50 to 5, it's 101.3. If you go from 25 to 2.5, it's 101.3. Oh, by the way, if you put different diodes in here, that's worth mentioning. If I put in, I don't know, a 1N4002 rectifying diode instead of these 914 switching diodes, you'd get the same kind of result, but you wouldn't necessarily, like in this case, get 101 millivolts. You might get, 97 or something, whatever. But the thing I want to point out here is the consistency. And I've also looked at factors of 2, right? 100 volts to 50, I get 30.5 millivolts. 50 to 25, I get 30.5 millivolts. I go from 10 to 5, I get 30.5. I go from 5 to 2.5, I get 30.5. I go from 2.5 to 1.25, I get 30.5 millivolts. We only start to see decent sized, kind of maybe getting obvious deviations when the input signals is getting pretty small, right? When we get down here where we're talking tens of millivolts, that's when things really start to deviate, right? So here's, the 101s, a 102, and then suddenly I get up to this 115 when I'm going from 100 millivolts down to 10 millivolts. Now, the reason for that is because of some approximations that are made in terms of the log current voltage characteristic. I go through this in some detail in the op amp textbook, the free textbook that you can download. No reason to really get it into here. The important thing, when all is said and done, the important thing is that when you look at this input, you're going from 10 millivolts to 100 to 100 volts, excuse me. That's a 10,000 to 1 change in input. 10,000 to 1, 10 millivolts to 100 volts. Yet the output is only changing from 183.8 millivolts up to 604.5 millivolts. That's a change of a little over threefold. 10,000-fold on the input gets squished down to a little over threefold, right? That's really, really compressive. Now let's flip this and look at the twin, in other words, the anti-log amplifier. So we can do the same thing, right? I put in 300 millivolts, and let's do a little DC analysis over here. And, we get 82.7. And I can repeat this process, which conveniently I've already done. So I jump to 330 millivolts, and look, this signal is roughly doubling from 82.7 to 166. I increase it by another 30 millivolts to 360, and I get 332.8, right? Just looking at the magnitudes here, right? It is an inverting amplifier. The minus is expected. So when I go from 300 to 400 millivolts, right, that's only a 33% change. Look, the voltage out went up by a factor of 10, 82 millivolts to 830 millivolts. You crank it up another 100 millivolts on the input, and it goes up by another factor of 10, right? We're over 8 volts over here. So from 300 millivolts to 500 millivolts isn't even a 2-to-1 change, but the output increased by a factor of about 100. That's really expansive, okay? Now, having said that, sometimes, a picture is in fact worth 1,000 words, or, maybe 2,000 words, or maybe 672,312 words. I don't know. But here's a little bit of a different circuit. What I've done is I've doubled up on my diodes. So I have one that can take care of the positive input and one that can take care of the negative input. So this is what I would call an atypical sort of arrangement. Usually with a sensor, you're unipolar, and what I was showing you a moment ago would be appropriate. But I like this because now you can visualize, you can have a good sort of visceral take on what this thing is actually doing. So again, I've got my anti-log cascade, so to speak. So this, what I'm calling V home, should be the same as the input, right? I'm saying we're going back home. But I've also taken this and run it directly through a clone of my anti-log amplifier, right? So I've got a log output here and an anti-log output. So this V-log should be this compressed version of the input, and V-anti should be this expanded version. And I'm just throwing a sine wave in here. I don't really care so much about what the amplitudes themselves are. I'm really interested in what the shapes are, so that you can understand when we talk about compressing a signal's range and expanding a signal's range. Now, for those of you that are, audioholics over here, this is a little bit different than when we talk about using, an audio compressor. That's not what an audio compressor is doing. That's a variable gain amplifier, the gain of which is controlled by the overall average input level. As the input level changes, the gain changes, and we sort of limit, if you will, no pun intended, what the range of output is, right? It's not just doing this. You try to use a circuit like this to create an audio compressor, it's not going to work, right? There's a lot more to it than just this. But in any case, let's do a quick little transient analysis, and you can see literally what I'm talking about. Open up. All right, so here's my input. Nice sine wave. Here's home. Remember, this is taking the log and then the anti-log, so it should look exactly like this. And then I've got my log output and my anti-log output. Now, yes, they are flipped. Just ignore that for a second, the phase being reversed. But look what's happening, right? So here's your log. It's compressive. So what happens? If you started this initial rate of change, right, which is way faster than what this initial rate of change is, and this wasn't compressive, then this signal would have gone up, 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 probably gone off the screen before it came back down. So this is squishing, and the higher the signal gets, the more it gets squished. So, it comes up and it gets like compress, compress, get the pliers out, and then, finally it starts to come back in. And this is what we get, this sort of, I won't call it a square wave, but it's, this sort of rounded off, like studded kind of stumpy looking sort of waveform. I think the anti-log waveform is particularly interesting. So you start off with, here's your like zero cross, and it's really quite pokey, right? This is really quite slow. And if you scaled that to, like this kind of change, right? Well, technically it would be this change right here, but look how fast this is, and this is really pretty pokey. But what ends up happening, right? As the sine wave's coming up, it starts to kind of, fade off. But this is actually like speeding up. So, if we had started off with this slope, the sine wave in here would have just kind of come in like this. Would have been really, you probably couldn't even see it with this sort of magnification. You'd have to really zoom in on this, right? There would be much. But what's actually happening is, as the signal's going up, it's getting more and more, it's like it's getting more and more gain, right? It's going up, 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 and you get this kind of like pimple, this little bumplet on the top, right? And that happens on both ends, right? Because it's symmetrical. So you can see it's kind of like, imagine that this waveform is just like made out of wire. Someone on the compressive side, on the log side, is like pushing down on the wire and it's squishing it and you're getting this, right? You're flattening it. On the anti-log amplifier, the expansive side, it's like you're yanking this up. So this gets pulled up. But if the curves, right, if the curves of the two devices doing the log and the anti-log are identical, then they perfectly compensate for each other, right? So one pulls up by a certain amount, the other, gets squished down by the same amount. End result, your output signal is identical with your input signal, right? Pretty cool. I think that's a really nice picture there. All right, so, we have these sort of basic log and anti-log amplifiers. They can get much, much fancier than this. Like I said, there are some issues with these by themselves. Temperature is a notable limitation, but this is a nice sort of introduction. You can get the idea of what they're going to be used for, right? So you need to squish down that sensor range, or you need to do the exact opposite, sort of zero in on it, expand it out. These are things you could look for, right? Log and anti-log amplifiers. You can have some fun math with your circuits. Okay, until next time, this is Professor Fiore saying, have a good one.